My name is Electron van Marle, and I would like to discuss the modeling of the interaction between an electron-positron beam and a thermal plasma. This is something I've been working on as part of the Gamma project, together with Ilya Plotnikov, Alexandra Markovit, and Claire Dupin. The problem that we're trying to solve is the origin of gamma-ray halos around pulsars. Observations initially by Hess and later by the high-altitude Walter-Cherenkov Observatory show TeV halos around young and middle-aged pulsars. This indicates that the local diffusivity for high-energy particles is low compared to that of the general ISM. This is likely caused by local turbulence. The question is, what is the origin of this turbulence? And one explanation, which was put forward by Evoli et al. In 2018, is that this turbulence is in fact self-induced by the high-energy particles that are trying to escape from the pulsar environment. And this is something that we wish to test numerically. This brings us to the problem of modeling the interaction between non-thermal particles and the thermal gas. Now we already know that it is possible for non-thermal particles to trigger instabilities and therefore turbulence in a local magnetic field, as shown for example by Bell in 2004. This is the same process that induces Fermi-1 particle acceleration in astrophysical shocks. Now whether this would occur under this specific set of circumstances, to wit the surrounding of a young pulsar, well, that would depend on the relative energy density of the non-thermal particles compared to the energy density of the local magnetic field. And we need numerical models of this process to determine whether it is a viable solution. However, this brings us to a very common problem. While astrophysical structures tend to be large, the interaction between particles and a local magnetic field involves physics on the microscale, and that creates a numerical problem. The two most common ways of modeling astrophysical plasmas are Magneto Hydrodynamics and particle and cell. And these are two very different approaches. Magneto Hydrodynamics, commonly known as MHD, is based on statistical averages, such as the mass, momentum and energy density of the local plasma. And as a numerical method, it is very good at modeling large-scale structures. It's computationally efficient and it can be scaled up easily. However, it cannot simulate microphysics because the very underlying assumption of magnetohydrodynamics is that the microphysics average out to create those statistical averages. By contrast, the particle and cell is based on treating a plasma as a collection of individual particles. As such, it can simulate microphysics and it can simulate a non-thermal plasma. However, it is computationally very expensive, making it difficult to model large-scale structures. It is also numerically noisy, which creates problems of its own. What we need for this kind of project is to take aspects of both these methods in order to get the best qualities of both combined into one single code. The method we use is referred to as particles in MHD cells, or PIC-MHD. It is based on the assumption that a gas can be described as a primarily thermal plasma with a relatively small non-thermal component. We then proceed to split the work. We take an MHD code, in our case the MPI-AMR-VAC code maintained by Ronnie Keppens at the University of Leuven, and we use that to describe the thermal plasma. Meanwhile, we introduce a separate module which uses individual particles to represent the suprathermal component. And these two plasmas, which exist in the same space and time, interact with each other through the grid. The MHD grid serves as cells for the particle and cell treatment. The interaction between the plasmas is handled self-consistently. On the one hand, the Lorentz force gives us the effect of an electromagnetic field as generated by the MHD on charged particles, and the effect of charged particles on the local gas can be described through a new version of Ohm's law, which was shown by Bai et al. In 2015. Now this method has several advantages. On the one hand, unlike traditional MHD, it can simulate particle acceleration and feedback. On the other hand, there is no need for a huge particle population to represent the thermal gas, which is the main problem with particle and cell. Of course, there are also disadvantages. For one thing, we work in a limited regime. As I said before, the underlying assumption is that the thermal gas has a much higher density than the non-thermal component. Now this is true for many astrophysical plasmas, but not for all, and it's something we have to keep in mind. A more severe restriction is that because the thermal gas is treated through MHD, there is no way of modeling the transition from thermal to non-thermal or back. So we always have to start with an underlying assumption as to the density of the non-thermal component relative to the thermal gas. So this is how it works in practice. We have a single grid where on the cell centers we define the MHD quantities, such as gas density, energy density, momentum density, and the magnetic field strength. At the beginning of each time step, we update these quantities through the conservation equations, which include the effect of charge and current from the non-thermal particles which exist in that same space, here represented by the little green dots. Then, for the same time step, we move the particles using a Boris pusher and based on the electromagnetic field which the MHD provides us at the cell centers. Once the particles have their new position and velocity, we use that to determine the charge and current density at the cell centers. Once we have this charge and current density at the cell centers, we're ready to take the next time step and once again use the conservation equations, including the charge and current density as generated by the particles, to once again advance the MHD quantities. We now wish to test this method on the problem that we're trying to solve, to wit, the presence of TeV halos around young and middle-aged pulsars. And we use a setup which is based on initial particle in cell runs, which were made using the Smiley code, which was introduced by Deruya et al. In 2018. We start with a homogeneous thermal background plasma, in which the alpha speed is 1% of the speed of light. And into that plasma we inject an electron-positron beam, which represents the particles escaping from the pulsar environment. For the particle density ratio between the beam and the background gas, we assume a density ratio of 10 to the minus 2. The drift speed of the beam as it moves through the gas is 10% of the speed of light, and the beam has a temperature of 10 MEC squared, which we calculate using a Maxwell-Jetner distribution. For the mass ratio between protons and electrons, we assume a factor of 100 because of numerical reasons. We have a relatively high spatial resolution of 40 cells per Larmor radius, the Larmor radius being the Larmor radius of the electrons and positrons in the local magnetic field. And we assume a beam particle density of 100 particles per grid cell, which is not too high, but this was due to restrictions because of our computational resources. For this kind of situation, the expected saturation, as calculated by Bai et al. In 2019, is given by the underlying equation, which I will not derive for you here. But for our input, we expect saturation in terms of the magnetic field energy at approximately 2.5%. Here we show the results obtained by the particle in MHD cell method for our test run. In this graph, we present both the velocities of the electrons and positrons as well as the magnetic field energy amplification. The green line shows the velocity of the positrons. The blue line shows the velocity of the electrons, both as a function of the alpha speed in the local medium. And as you can see, after initially starting at 10 times the alpha speed, which is what we injected, the velocity of both components drops relatively quickly to approximately the alpha speed. However, there is a velocity difference between the two, with the positrons on average being faster than the electrons. Meanwhile, the kinetic energy of the beam is being transferred into magnetic field energy through instabilities that are triggered in the local magnetic field. As can be seen here, the saturation of the magnetic field energy peaks at approximately 2.5%, which matches the analytical prediction. As to the difference in velocity, this was unexpected. However, particle in cell runs done with the Smiley code actually achieved the same result. As can be seen here, the velocity of the positrons in the beam is on average higher than the velocity of the electrons. To conclude, our initial run was successful in that the results agree with the analytical prediction for the magnetic field amplification. However, there are some problems. One thing we have learned is that high resolution, both spatially and in terms of the number of particles, are required for a good result, and we're going to have to redo these simulations on a larger computer in order to get a higher number of particles per cell, which will result in a smoother result. We've shown that the presence of an electron-positron beam can trigger instabilities in the local magnetic field and therefore create turbulence, which seems to indicate that indeed these TeV halos around pulsars can be created purely because turbulence is being induced by the high energy particles themselves without an external source. What we need to find out right now is what causes the difference between the electron and positron velocities. One possible explanation is that this is due to the background plasma, which consists of electrons and protons. So there is a mass difference in the positive and negative particles in the thermal plasma, but not in the non-thermal plasma, which can create a difference in how they react as the magnetic field starts to move. For the future, we're going to increase scale and resolution of our simulations. What we're also going to do is add a non-thermal proton component to the beam, because there are more than just electrons and positrons trying to get away from the pulsar. And with this, I end my talk, and I thank you for your attention.